So in this tutorial, we're going to talk about radioactivity and nuclear decay. So the first thing you really need to know is that when we talk about nuclear reactions, they are reactions that occur at the nuclear level. So reactions that occur at nuclear level. Now, when we talk about the word nuclear, nuclear and nuclear level, just know that we're talking about things that happen to the nucleus of an atom. And so there are three types of nuclear reactions, and the first one is radioactive decay. The other two are fission and fusion. Now, fission is when you have something that's a large nuclei, so a large nuclei that is broken down. So large nuclei that is broken down into smaller nuclei. An example of this is uranium being bombarded by a neutron. So I'm just going to go ahead and show you an equation plus uranium, 92, 235, uranium, and it becomes smaller particles, 142, 56 barium, and 9136 krypton, and another neutron. So here's just an example. This is an example. And this is the type of energy that is produced in nuclear reactors today. And this is a process called fission. Now, fusion, on the other hand, is a different story. It's when two nuclei join together to form a large nucleus. I said larger nucleus. And an example of this would be two hydrogen atoms, or I should say two hydrogen isotopes, so 3, 1, and you end up with 4, 2 helium. Oh, sorry. 1, 0 neutron. And so this is actually the type of energy produced by the sun, and it's through fusion. And it requires high temperatures. So, but in this tutorial, we're going to focus on radioactive decay. Radioactive decay is the spontaneous disintegration of nuclei into a slightly lighter nucleus, and particles or electromagnetic radiation are always emitted by these types of radioactive decay. One thing I do want to add, when we talk about spontaneous disintegration, it's not like the nucleus is going away, it's just you're breaking down. So a better term for this would be a breakdown of a nucleus. And the particles we'll learn, the two types we'll learn are alpha, beta in this tutorial, and the electromagnetic radiation that is emitted is a gamma ray. If you've had a introduction to electromagnetic radiation, the term gamma ray should be very familiar. It is a type of wave that is in a form of energy. So let's go ahead and talk about how these are all related to radioactive decay. Just to reiterate, here's a nuclei. And when it goes through a spontaneous decay, it emits a particle. So here are some of the particles. Here's the alpha and here's a beta. And you end up with a lighter, more stable daughter product. So let's go ahead and this is some of the examples I'm going to show you as a picture of this process. So alpha emission is when you have too many protons in the nucleus. So when you figure out the radioisotope that you have, you make sure that you have to do the N to Z ratio. And depending on their N to Z ratio, you'll know whether they have too many protons and too many neutrons. And if they have too many protons, you end up with having an alpha particle. Now, this particle that's emitted is typically the helium atom without any protons. So if we look at this, we have plutonium. And if you do the N to Z ratio, you'll realize that there are too many protons in the nucleus, and it doesn't fit in the band of stability. So when you take this, you're going to go ahead and go through an alpha decay. And when that happens, you end up losing a helium, so 2 protons and 2 neutrons. Oops, 2 neutrons. And that tells me the new atomic mass. So helium has an atomic mass of 4 because atomic mass is the number of protons plus the number of neutrons. Since that's the case, I know that my plutonium has now lost the 2 protons, which is 2 less atomic numbers, and I end up with uranium. Since I lost 4 atomic mass, my uranium should have a new atomic mass of 236 and a new atomic number of 92 because I lost 2 protons. Now we're going to write chemical equations for these decay process. So again, just remember alpha emission is when you have too many protons in the nucleus. And to determine that is you need to take the N to Z ratio, so the number of neutrons over the number of protons. And you'll know that you'll have to go through an alpha decay. And so if you look at the atomic number and atomic mass, atomic mass, atomic number, you know when you go through the alpha decay, you're going to emit a helium atom without any without any electrons, and and you end up with a lighter product that has 2 less protons, so it has now a new atomic number of 90, and also lost 2 neutrons, so its atomic mass is now 234. So let's go ahead and take the alpha decay of acetine 209. So if we look at 209, and the atomic symbol for acetine is At, and the atomic number of acetine is 85. When it goes through alpha decay, it's going to go ahead and spit out a helium atom. And it's also going to be 2 protons lighter and 2 neutrons lighter. So it's going to have a new atomic number, which is going to be 85 minus 2, which is 83. And it's going to have an atomic mass that's 4 particles lighter. So it's going to be 209 minus 4, which is 205. And if we look at the periodic table, the element with the atomic number of 83 is bismuth, and it has the atomic symbol of Bi. Then this is how you would write a chemical equation. Now, if you notice, in the first equation, helium was written second in my reaction side, but it's written as the first reactant first product in the product side. Sorry, I misspoke. It doesn't really matter whether you write helium first or helium second. It really, just as long as it's present in the product side of the chemical reaction. Now, beta emission occurs only when you have too many neutrons in the nucleus. And what happens is you end up having a neutron converting into a proton, and you eject a beta particle, which is just an electron. So it's written as O minus 1. And I'm going to go ahead and give you an example. If you have a atomic mass of, for let's say fluorine. Let's take fluorine as an example. And fluorine has an atomic number of 9, and let's say it has an atomic mass of 20. Okay? This means I have a number of protons. My number of neutrons for fluorine are going to be 9 and 11. But what happens, and again, so I have too many neutrons, and so I have to go through a beta emission, and my number of neutrons convert into a proton, meaning that I end up losing a neutron and gaining a proton. Now, my atomic mass is still 20, since atomic mass is the number of protons and the number of neutrons. So our atomic mass is going to retain the same, but what happens is all we're doing is a conversion of this neutron to a proton. And an example of this would be radon. Here's 228 radon. And it has an atomic mass of 228 and atomic number of 88. Now, this is going to end up staying the same because if you look at this, our number of protons and our number of neutrons. Here is my number of protons for radon, which is 88, same as our atomic number. And the number of neutrons is 140. If I convert one of my neutrons into a proton, I lose a neutron, and that's 139, but I gain a proton, so it's now 89. Again, my mass should still be 228. Nothing has changed with my atomic mass, but now my atomic number has changed. My number of protons have changed, so now I am a new element. And here's my beta particle. It just ejects an electron. So if you want to take this into consideration, here we're going to go ahead and do some chemical equations dealing with the radioactive decay of beta particles. So here's iodine 131, and it has an atomic number of 53. I will convert one of these neutrons into a proton, and now I have a new element, xenon, and I eject a beta particle. The beta particle is always written as 0, -1, and an E. Well, there is another way you'll see it written. Sometimes it's written 0 and -1, beta. They are the same, but in this tutorial, we're going to be consistent with this type of writing for the beta particle. So let's go ahead and talk about the beta decay of carbon-14. So carbon-14 has a atomic mass of 14, and there's a symbol of carbon, and it has an atomic number of 6. Remember, we gain a proton, so it's 7, but atomic mass doesn't change. We are now no longer carbon, but we are nitrogen. And we also lose an electron. Now, I can also write this as, remember, it doesn't really matter which order I write this. I could have written it as 0 -1 E, the beta particle, plus the 14, 7 nitrogen. Just as long as both of them are in the chemical equation, then you are good. They're both accepted. Now let's finally talk about gamma emissions. Gamma emissions are just high energy electromagnetic waves, and they're emitted in all decay process. They're all energy. And so this is always going to be a byproduct of any decay process. And its symbol is 0, 0, gamma. People think of this as the upside down fish. And the reason why it's 0, 0, gamma is because it doesn't affect the number of neutrons, nor does it affect the number of protons, and it doesn't inject anything except for just energy. And so it really doesn't affect your product. So let's go ahead and do a couple of examples. If you want to try these examples, you can pause here, write it down on a piece of paper, and check if your answers are the same as mine. But I'm going to go ahead and do these examples with you. So the first one is alpha decay of astatine. And so if we do the alpha decay of astatine, we're going to write 209 AT. So the mass is 209 AT, and it has a atomic number of 85, and it goes through alpha decay. So I'm going to go write the 4,2 helium, and that means it's no longer 209, but it's 205 because we lost 4 of the atomic mass, and we lost 2 protons, so it's now 83, and it is bismuth. Let's look at the beta decay of potassium. Potassium has an atomic mass of 40 K, and the atomic number is 19. If we go through a beta decay, which is 0 minus 1 E, we gain a proton and keep the mass, and our new element is calcium. Here's beryllium. So beryllium-7 has an atomic mass of 7. Be is a symbol, and it has an atomic number of 4. If it goes through a beta decay, I'll write 0 minus 1 E. We gain a proton, so the new atomic number is 5, and the atomic mass stays the same. Our new element is boron. And finally, here's our last example, alpha decay of oxygen. So oxygen 19 has an atomic mass of 19. It has a symbol of O, and the atomic number of oxygen is 8. And if it goes through an alpha decay, so 4,2 helium, I lose 2 of my atomic number and 4 of my atomic mass. So I should have 15 and 6. My new element is now carbon. I do hope this tutorial is helping you out, and so I'm going to do a quick summary table. And in this summary table, I'm going to go, I would like you to write down. So in this table, you are going to have the types of decay, so alpha, beta, and gamma. And the particle alpha emits is going to be 4,2 helium, the helium atom without any protons. Now, when it goes through a decay, you lose 2 protons. So that means we have a change. So we decrease, so lose 2 protons. So our atomic number decreases by 2. And remember, we lose also 2 neutrons. So our atomic mass will decrease not by 2, but by 4. Decreases by 4. Okay. Beta, the beta particle, when we go through beta emission, is 0 minus 1 E. And what happens is that we don't lose a proton, we gain 1 proton. So our atomic number increases by 1. And our atomic mass does not change. Does not change. So I'm just going to put an X because it doesn't change. And finally, gamma particles. Gamma particles, the symbol is 0, 0, and that upside down fish. And it doesn't affect the the change in the proton. So we end up having no proton change, no neutron change, and our atomic number doesn't change, and our atomic mass does not change because of gamma particles. So I hope this tutorial and this summary has helped out, and thank you for watching this tutorial.